All right, well, let's go ahead and start here on this next video. Um, this will be a long section of notes. I'll probably break it up into several different videos, but I really like teaching this part of the class because it's all about chromatography and instrumentation for chromatography. I find it really, really interesting. And it's important because chromatographic separations are really a very important tool in the modern analytical laboratory. So I like telling you all about them. Now, this is a huge field with many thousands of research papers published every year. So I'm only going to be able to give you an overview of chromatographic separations, but nonetheless, that'll at least get you started and provide a base building block for you to professionally develop upon. So as always, we're going to have some key terms. I'm going to try to highlight them in red and blue text as we move through this section. And we'll also have our learning objectives. We can use this as a study guide. These are basically the things that I want to cover and have you know in preparation for your final exam in this course. And of course, we will test over chromatographic separations on that final exam. So as I mentioned earlier, chromatography is literally color writing. Okay, and there's two types of chromatography, liquid and gas. I'm going to start telling you about gas chromatography first, and then I'm going to come back and tell you about liquid chromatography second, okay? So the first section is all about GC, which stands for gas chromatography. I don't want you to lose sight of that. I don't want you to be confused and just mentally file all these things together because these are really different techniques. In gas chromatography, your mobile phase will be a gas. This is also called a carrier gas. This is your mobile phase in GC, okay? It's a gas. Oftentimes it's helium, sometimes it's nitrogen, but generally speaking, whatever we use, we want it to be an inert gas. We do not want it to react with the analyte, nor do we wish to react with the column. It has to be inert, chemically inert, not reactive, okay? Now, this technique in general is used to separate what is called volatile compounds in mixtures. Now, volatile, we throw that word around a lot. What does it mean, right? Sometimes people think that means it's going to kind of catch on fire and explode. Sometimes volatile compounds may do that, but that's not the way chemists use that word. When a chemist says something is volatile, basically what that means, go back here. I'm not even sure if this is showing on my screen anymore. Let me come back to my Zoom meeting. There we go. When chemists use the word volatile, what we mean by that is that it has a high vapor pressure. Essentially, that means we can evaporate it and get it into the gas phase. So this technique will separate these components by basically differentially evaporating them based upon boiling point and also based upon some interactions that they can have with the stationary phase, and we'll get to that. But an overview for how this works, we're going to inject either a gas or a liquid into our chromatograph. The chromatograph is the instrument that we're going to use for GC, block diagram shown at the bottom. Usually, analytes for GC are organic molecules of intermediate or high volatility. Again, that means we can get them to go into the gas phase easily. If you can't get something into the gas phase, GC is not the technique to analyze it. So for instance, ionic compounds like sodium chloride, you would never think about analyzing an ionic compound by GC because they have extremely low vapor pressures. You can't get it to pass into the gas phase at all. So yeah, ionic compounds is not the realm of GC. GC, you can separate organic compounds of intermediate or high volatility. The way this works is we're going to take our sample, either gas or liquid, and we're going to inject them into the instrument through a small injection port by piercing a rubber septum. As soon as we do that, this whole region of our apparatus is kept at a pretty high temperature, which vaporizes the liquid. So anything that's a liquid that's injected in will get flash vaporized, essentially immediately. We'll use a carrier gas. Oftentimes that's helium. That's our mobile phase, okay, to sweep the injected sample through our column, which is again a long tube. There's a couple different types of these tubes that are used in gas chromatography. I'll talk about the construction as we go on. Some of them have an open bore and just have the stationary phase coated on the inside of the tube. And others are fully packed, okay, where the gases actually have to percolate through a packed column. So different column technologies, we'll get to that, okay? But this inert carrier gas, the mobile phase, will sweep our molecules through this tube from the inlet of the column out to the outlet where a detector is placed. Now, because different components will have differing volatilities, different tendencies to pass into the gas phase, and also different tendencies to absorb to the stationary phase material, they will move at different rates through this column. They won't all move the same. Some will be retained by the stationary phase, some won't. At a particular temperature, if we don't have the temperature too high, some of our molecules may be slowed down because they might condense a little bit more than other molecules. So we can achieve separation. Molecules will be detected at the end of the column at a detector that we'll have to build, and we can build our chromatogram, our plot of detector signal in time. This is a gas chromatograph, okay? I've described a lot of the parts as I've been narrating, but one thing that I forgot to describe to you, okay? I think I may need to move up a little bit there, is that the entire column is placed within an oven, which is really important in GC. We're actually going to heat this column up to a reasonably high temperature. And the purpose of that is to get our materials to vaporize, basically, okay? Gotta have your column, gotta have your column within an oven. And that oven really needs to have the ability to precisely control the temperature. Because if you can't precisely control the temperature in GC, boy, you're in a world of hurt, because you're going to get highly variable retention times, and things aren't going to be easy for you from there, okay? Okay, so let's move on. Let's talk about more instrumentation here for GC. And I want to break down each of these individual parts in a little bit more detail, okay? All GC instruments, regardless of the make, manufacturer, model, is going to have a way to introduce a sample. That's going to be called the injection port here in a second. All GC instruments are going to have a column which contain our stationary phase. That's that tube with the stationary phase. Some are packed, some are open tube. We'll get to that. We're going to need to have an oven to maintain precise temperature control and some way to detect or analyze once they elute through the column. Now, individual GCs are all a little bit different, but they all have those parts. Let's break down these parts in a little bit more detail. I mentioned that all GCs need to have a way to introduce our sample. This is called the injection port of the gas chromatograph. The way that this works is we generally take a syringe, okay, it's a gas-tight syringe with a needle on the end. A sharp needle, got to be careful with it, right? And we draw up a small amount of sample. Oftentimes it's measured in the microliters or even low microliter range, like 1 or 2 microliters is generally a lot for this experiment, okay? And we draw up that fluid, very small volume, inside the syringe. And then we place the syringe through a rubber septum. So this septum is basically just like a little piece of rubber that seals the inside of the instrument off from the outside. And we can pierce it with the syringe, and that allows us to get the sample inside. And when we draw the syringe, that septum is supposed to close back up. Sometimes they leak and you have to replace them. It's kind of something that you have to do to maintain your gas chromatograph, okay? But we're going to pierce that septum and deliver our sample into this region of the injection port, okay? Now, inside the injection port, we're going to hold that whole apparatus at a high temperature, here about 350 degrees Celsius. Generally speaking, you want to hold your injection port temperature at a higher temperature than the highest boiling component of your mixture. In other words, the temperature here needs to be higher than all the boiling points in your mixture. The reason being is if that's the case, you immediately flash vaporize your material. You want to achieve that. As soon as you inject your material into the GC, you want it to vaporize into the gas phase. so that it can quickly get swept onto your column, which is right down here at the bottom, okay? You want to quickly sweep that material onto the column. You don't want it to stay in the injection port very long at all. So we purposely make it very hot so that happens, okay? Now, there are a couple figures here that I guess we should talk at least a little bit more about. And these are all different designs of injection ports. There's on-column injection, splitless, and split injection. I started to use the split injection figure just to kind of give you a background. But now I'm going to get into a little bit more details. So what I want to do is look at the details of this first case, the split injection. It turns out that this particular apparatus is essentially a way or a means that chemists or analysts can like purposefully waste some of their sample. And that sounds crazy, right? Why would you want to purposely waste some of your sample? Well, it turns out even if we inject like 1 or 2 microliters of sample onto our column, sometimes that's too much if we're using a very, very highly sensitive detector system and a column that has a limited capacity to handle sample. So we got to basically purposely get rid of some because we can't inject less than this. It's already a tiny volume. It's kind of our technical limit in terms of what we can inject from the outside world. So what we do instead is we use a split injection scheme. And the way this works is you provide your carrier gas flow in through this port right here. Okay. Now, in this particular figure, it's suggesting 102 milliliters per minute total. And I'm going to explain where that 102 milliliters per minute goes here, okay? The first milliliter per minute, this flows out the other side. This is called the septum purge, the septum purge. It's a relatively slow minor flow of gas, basically just right across the inside surface of that septum, okay? The reason why the septum purge is important and oftentimes used is, first off, it keeps the septum from just getting too warm, too hot, and starting to melt and degrade. Okay, we wouldn't want that. It would cause all sorts of trouble. We'd always have to replace it, and that'd take a lot of time, right? But another thing the septum purge does, when you pull that needle back out to withdraw it, sometimes you can get just a little bit of material here on the inside of the septum, where it's a little bit cooler, and we basically don't want that to slowly bleed onto our column. So the septum purge will kind of sweep some of that back out to waste. Okay. And gets rid of it. So that's the septum purge. It's a minor flow, only one part out of 102, right? Now, where does the rest of this 102 milliliters per minute go? Well, it goes down this way also, okay? Now, into this mixing chamber area where it's mixed with our sample. Now, we inject it, and then it flows out towards the bottom. Now, 1 milliliter per minute, thereabouts, gets introduced to our column. And the other 100 milliliters per minute goes out through this vent to the outside world, essentially to waste. And that's the major flow, 100 milliliters per minute. So out of 102 milliliters per minute, only about 1 milliliter per minute flow rate gets onto our column. Most of it ends up being wasted. So we call this a split injection scheme. And again, the purpose of this is to sort of come up with a reproducible mechanical way to reproducibly split our sample so that we can, from run to run to run, get the same split ratios, and we're able to reduce our sample volume down to something that our column can handle, a much smaller quantity, okay? Split injection. Sometimes you run those split injection. There's also splitless injection. And this is where you do not do that, okay? Same injection port, except now we're going to use 2 mil per minute total flow into this chamber. We flash vaporize everything. 1 mil per minute goes out to the septum purge. 1 mil per minute goes onto our column. We basically close that valve off. There's no split vent this time. Okay, that's a splitless injection. And then lastly, there's on-column injection. This is where you would actually take your syringe and place it right at the entrance of the column. This is actually your chromatographic column. Dispense your fluid and you inject it all basically directly onto the column. That's called on-column injection, okay? So different designs for injection ports. Different GCs have different designs depending on their requirements. And if you ever do this in lab, you'll have to kind of do a little bit of homework and investigation to figure out which one your particular device uses. Now, just as there are multiple different injection ports, there are also multiple different types of columns, okay? We've got two major categories. One will be called the pack column. Those are these two shown here on the left. And the other one is called the capillary column, okay? They differ completely in construction, as it turns out, okay? So let's talk about these for a second and some of their characteristics. We'll start with pack columns, which are the two on the left. Pack columns are either a stainless steel tube, which is most common, okay, shown like this, or a glass tube, which is a little bit less common, around a couple millimeters in diameter, okay? And inside those tubes, you basically pack the entire tube or fill the entire tube with stationary phase material, hence the name packed column. Okay, so the mobile phase gas, the carrier gas, actually has to kind of percolate through this column around the particles as it traverses from one end of the column to the other. Okay, these are our packed columns. Now, that stands to reason, okay, well, what do you use inside the column as the packing? Okay, well, usually you would use as a base particle. Okay, again, there's literally millions or billions of particles that make up this packing, like a diatomaceous earth type material. And sometimes you would just stop there and it would just be a solid that's pretty inert, a surface for molecules to adsorb to, basically. And if you did that, you'd be doing what's called gas solid chromatography, GSC. In that case, the stationary phase is just a solid particle, and the gas phase, your mobile phase, is in the mobile phase, right? Now you can also do what's called gas liquid chromatography in packed columns. And here what you would do is you take a very similar solid support like this diatomaceous earth material, okay? And then on the surface of that, you would put a thin layer of coating. And that coating would be a liquid phase. Now, you got to be a little careful with what you use for your liquid. Okay, you cannot use something that has a low boiling point, because if you did, remember, we're going to put this column inside of an oven and we're going to heat it up, aren't we? Right? And when we heat it up, if that liquid has a low boiling point, well, it's going to all evaporate. So we need that liquid to have quite a high boiling point, which we can achieve through careful choosing of our liquid, what material we're going to use. So high boiling point liquid will coat that solid support with thin layers. And then what can happen is if I have a molecule floating through my column, it can basically collide with that stationary phase and dissolve into it before it re-evaporates and moves its way down the column, okay? So that liquid serves as our stationary phase. But nonetheless, in either case, packed columns, they take these solid support particles and they pack it into that column. They fill that column up completely, and gas molecules in our carrier gas have to percolate between the particles to make it work. Now, the other thing is the capillary column. This is the other fundamental design for how the column technologies work, right? Capillary columns are still tubes, but boy, their characteristics are really, really, really different, okay? The capillary column internal diameter, or ID, is well less than 1 millimeter. Oftentimes it's half a millimeter or less than that even, okay? So tiny, tiny, tiny bores, very, very small bore columns. Difficult to see unless you look at the under a microscope. And they're actually made out of a glass called fused silica. And they produce these by taking a glass tube, heating up a section, and then basically pulling it very, very carefully down to very, very small internal diameters. The outer diameter is usually somewhere around 400 microns. And you can see it looks brown. That's actually the glass tube. And they coat it with something called polyimide, which actually gives the tube really interesting properties. You would think that such a small bore glass tube would be very, very fragile. But actually, as long as it's coated with the polyimide, that polyimide sort of gives it some strength, and you can actually coil it up like you see here. What you're looking at is actually probably a 30 to 60 meter long tube, just wound around basically a copper spindle. just wind it and wind it and wind it. But the total length of the tube is huge. You're almost talking about half a football field here. And that's another big difference between capillary columns and PET columns. PET columns at most might be like 2 or 3 meters in length. But capillary columns much longer. Usually the minimum length is about 30 meters. Maybe you can get down to 20, but 30 is pretty common, okay, as a minimum. Completely different length scale between these two columns, completely different construction, okay? So hopefully you can start to appreciate now that these two columns are going to be used for different things, and they're going to also offer different performances. So on this slide, I guess before I go on, I don't think I'll talk more about PAT column technology. So I did want to mention that PAT columns can offer somewhere around 10,000 theoretical plates, okay? And that's actually quite a bit less than we'll see for capillary columns, but I do want to mention that now so I don't forget. Now, what about capillary columns? These are the ones made out of those glass tubes that are basically coiled and 30 to 60 meters in length. Well, they offer much better performance. We can actually achieve up to 200,000 theoretical plates. Because these capillary columns are small glass capillary tubes, way under 1 millimeter internal diameter, and they're open tubes. So we actually coat the stationary phase on the inside of the tube, and really only the inside of the tube. That's where we're going to coat that stationary phase at, okay? And there's a couple different ways to do that. One is to create a WCOT, or a wall-coated open tubular column. And if we're going to do that, if we're going to create this type of column, we coat a thin layer of stationary phase right on the inside surface of our tube, the whole tube from start to finish. Thin layer of stationary phase on the inside. If we do that, that is a wall-coated open tubular column, as the name suggests, okay? Now, typically, this stationary phase film is not so thick, maybe a micron or so. It turns out if you make it too thick, you can degrade the performance, okay? So just a very, very thin layer on the inside of the column. The other way that we can put our stationary phase on the inside of an open tubular column, as is a capillary column, is through a support-coated approach, SCOT. This is very similar. We're still going to affix the stationary phase to the inside bore of our tube, okay? These are end-on views of our tube, right? So the stationary phase is still going on to that inside, okay? But the difference is, before we put the stationary phase on the inside of the tube, what we're going to do is we're going to add support particles there. These are basically like those inert particles like I was telling you about in the PAT columns, like a diatomaceous earth, something inert that we can stick to the inside. Usually, micrometer size type particles stick to the inside of this tube. And then we come back and we coat the stationary phase onto the support materials, okay? So why would we go through all that trouble? There's a pretty good reason. The reason is it increases the surface area. It increases the surface area of our stationary phase, because now we're not just coating the inside of the tube, we're coating all of these surfaces present on the support particles, which can yield a pretty significant increase in total surface area. And if we increase the surface area, that offers the advantage of having essentially more stationary phase present. And if we have more stationary phase present, we can actually inject more sample prior to our column being what's called overloaded, which means that we're just injecting too much sample. It can't reliably partition between phases in an equilibrium sense, and that really degrades separation performance. So by increasing the stationary phase surface area, we really can get around that, all right? And that's what it's for. Now, the last approach to column technology for these capillary columns is the porous layer open tubular column. It's an open tube again, but on the surface of the inside of the tube, we engineer a porous layer. That's actually a solid, okay? An example of which can be shown right here in this figure. What this is an electron micrograph of the inside walls of one of these tubes. Down here, is the glass or the fused silica. Okay, so that's actually like I was to take a screenshot of that from a side-on perspective. Okay, so we can see the tube itself, and on the surface of that tube, what they have deposited here is a porous layer of carbon. They just deposited it here. You can kind of see it right here. Right, it's a different material, thin porous layer around 2 micrometers thick. So actually quite thin, right? 2 microns is not very thick. It's a scale bar down here, right? So that porous layer can serve as the stationary phase for GC. And then, of course, here is the internal bore of a column. That's where the carrier gas would pass and our sample would pass, right? Like in through here. So these are typical column constructions that people have come across over the years for capillary GC. Now, as I mentioned, these columns, the PAT column and the capillary columns, will really behave a little bit differently, okay? They're constructed differently and they have differences in performance. So in terms of PAT columns, well, they typically might have internal diameters of 3 to 6 millimeters, 6 being pretty large, okay? But these capillary columns are much, much, much stronger or smaller. The capillary columns might have internal diameters down to 0.1 millimeter, that's 100 micrometers, up to about 0.53 millimeters. Okay, that's actually called a megabore column. PAT columns have short lengths of 1 to 3 meters, but capillary columns, gosh, 30 to 50, I've even seen 60 meters. Capillary columns are much longer, and they have narrower bores. The particle diameter that's in a PAT column, well, it's maybe 120, 185 micrometers. Remember, sometimes you can coat that with the liquid stationary phase, but the particle diameter which packs these capillary columns, see, look, there's no entry here. And that's because they are open tubular. They're open tubes, aren't they? Okay, what about the coating thickness? This is the stationary phase on the particle, okay? Well, for these capillary columns, 0.1 to 0.5 micrometers. It's a little bit thicker potentially for the PLOT. You know, that's where they have the porous layer on the inside. The one we saw was 2 microns previously, but remember, you don't want to make that film too thick. What about performance? The number of theoretical plates total and per meter, somewhere around 1 to 5,000 theoretical plates. Now that's the end. Remember, bigger is better for that, right? Higher end is better. But for the open tubular capillary columns, we can achieve much higher performance, 25,000 to 200,000 theoretical plates. Okay, so it turns out that capillary columns are used for most high performance analytical work, because you get much higher number of theoretical plates, much better narrow peaks. Now, what about how much sample we can inject? Micrograms of sample component. Well, for the PAT column, I can inject maybe up to 100 micrograms max. But for these capillary columns, look at this, way small amounts. Small amounts of sample only, please, right? If you inject too much, you overload your column, you're not going to get a very good separation as a result. However, the PAT columns are more tolerant. You can inject much more sample before having to worry too much about loss of resolution. Typical flow rates in milliliters per minute, which are involved. PAT columns, 20 to 100 milliliters per minute, but look, much slower flow for the capillary columns. This is because they're smaller tubes, right? So we don't need as high a flow rate through these. So in general, the capillary columns, the open tubular ones, are used for high performance GC separations. But the PAT columns are generally a little bit less expensive, and in addition, they offer the advantage of a higher sample capacity. Okay, you can inject more sample, but that's usually not terribly important for GC work. But the reason being, you know, you can always split your sample at the inlet. So the sample injection volume is, you know, usually not a crucial parameter when you're, you know, considering a technique. You much rather have the better performance. Okay, So what are some typical stationary phase materials? Okay, we hadn't talked about what that stationary phase is made out of yet. Maybe we should do that. And this is a table that's reproduced from your textbook, okay? Table 22.1 here in my slide. And what this basically shows us is a series of different stationary phases for gas chromatography. Now, many of these are going to be based on what's called the siloxane linkage, And I want to highlight that first. So what that is, it's basically a polymer of silicon oxygen. The oxygen, silicon, oxygen, silicon, over and over and over again, a long chain. But here's the thing, silicon, like carbon, can form more bonds. It can really form 4. So what we can do is we can derivatize these silicons in a long chain with different groups, maybe R prime, R double prime, R triple prime, right? So we build these long chains of silicon, oxygen, and then we just bond other things to the silicons, okay? Sometimes I call this like the shrubbery or the landscaping, okay? And if we're gonna make one GC phase different from another, basically what we're gonna do is we're gonna attach different R groups, and that's all they do. So this backbone of silicon oxygen is called siloxane. And what we're gonna do is just make different R groups. Now, what's the point of that, okay? Well, if we change the R groups, what we're functionally going to be doing is we have at least the ability to change the polarity of our phase, change the polarity of our stable phase. And that's why we would tune these R groups. Another thing that's great about the siloxane linkage is since you can form it in long chains, the resultant polymeric molecules have very high molecular weights, very high boiling points. So they're not very volatile. So you can heat them up, they won't degrade, and they're not going to evaporate and go anywhere either. Okay, so what is like the simplest phase we can come up with? It actually would be this one here. And forget about this for a second, okay? But let's just say that we took this group in parentheses and copied and pasted it over and over and over and over and over again. Copy and paste, copy and paste, copy and paste, right? On and on to make a long chain. If we did that, we would have what's called polydimethyl siloxane. This is abbreviated oftentimes PDMS. Polydimethyl siloxane. That's basically like silicone caulk. You might buy a high-grade caulk at the hardware store, okay? And it turns out that you could make that with all methyl groups, these all being CH3 groups. Nothing wrong with that. And if you did, that resultant GC phase would be really quite non-polar. It would be a very, very non-polar phase. In fact, just about the most non-polar phase that you could make. So you might expect other analyte molecules that you're trying to separate, which are non-polar, to adhere or stick to that phase, perhaps. Right? And that would be something that we might expect, right? Just from like dissolves like type of principles. So what else can you do with these R groups that are bonded to the silicon? Well, if you want to, you can substitute a certain fraction for other groups. Like here, notice they added these phenyl groups. Down here, they've got some methyl groups, but they've got a phenyl group here, and up here, they have something even different. Look. This is called cyanopropyl group. C triple bond in here at the end. And that's actually introducing some significant polarity into our stationary phase. Now, if you want to make your phase more polar, what you can do is start adding some of these phenyl groups or cyanopropyl groups at different mixing ratios. And you say the phenyl group, that's not really a polar group, right? I mean, I don't see any O bonds, or there's no fluorines or chlorines. There's not any highly electronegative elements. Right? It's kind of this phenyl. It's not polar, right? But these rings, the delocalized electrons, have a pretty high density of negative charge. And as a result, there's a little bit of a local polarity there, a little bit of a a negative charge density, we'll say. And that can certainly, through intermolecular forces, interact with analytes and help retain things. Now the cyanopropyl group formalizes things with this CN triple bond. Nitrogen is pretty electronegative, isn't it? So that carbon nitrogen triple bond, that group is quite polar. And as a result, if we start introducing cyanopropyl groups, we're making our phase much more polar than it otherwise would be. Now, these are kind of like the base units that we might build, methyl, cyanopropyl, phenyl. We can build our GC phases out of that. But in addition to changing the groups, we can also just change the mixing ratio. In other words, we can change the percentages of the side groups of these landscape groups from 100% methyl to all the way to 100% cyanopropyl if we want to. We can make them all methyl, we can make them all cyanopropyl, we can make them all phenyl, and then anywhere in between. So there's a lot of tunability, isn't there, with respect to these GC stationary phases. And indeed, when manufacturers make these, a lot of times they give them unusual trade names like OV1, OV19, et cetera, et cetera. But if you do a little bit of digging into their product literature, you'll quickly find that they're all based on the siloxane linkages. And all they've really done is sort of tune the shrubbery, tune the landscaping a little bit to make their phase a little bit more polar or a little bit less polar. As a general rule, you want to use a polar stationary phase for polar analytes, because they will be retained more on that polar stationary phase, okay? Now there is one more type of phase that I want to tell you about. It's the one I'm circling right here. It's a strongly polar phase, very, very polar. It's just based on a different chemistry, so I haven't talked about this one. The others are based on the siloxane linkage, this one's not, right? This one is called Carbowax, kind of its trade name. They all, again, have these weird trade names associated with them. But what a Carbowax phase is essentially polyethylene glycol. Okay, it is this repeating CH2 is H right there, okay? Oh, and I'm going to basically copy and paste that n times to make a long chain polymer. This is Carbowax, okay? This phase, sometimes you need to see that thrown around, particularly with PAC combs. It's a strongly polar phase, and many times people will buy this Carbowax comb to separate molecules, small organics, which are polar. Okay, you'll see that in the PAC comb technology a lot. But nonetheless, this is the different palette of materials which make up our stationary phases for GC. Now, the exact stationary phase polarity is kind of important in GC. There's really two factors that affect separation, okay, if I'm going to be honest with you. And the two factors that are affecting our separations in GC, the first one, probably of primary importance, is the boiling point of the analyte in question. The higher the boiling point of the analyte, the longer it's going to take to elute. So usually, low boiling point equals fast elution. High boiling point is slower elution. So as a general rule, that's true. But the second thing that can affect the speed or rate at which a molecule moves through our tube is, of course, going to be our interactions with the stationary phase. Now, as our analyte has stronger and stronger intermolecular forces for the stationary phase, dipole-dipole type forces, right? Polarity-based forces. Stronger intermolecular forces will lead to increased retention and slowing down the material as it moves through the column. So I think boiling point, I'll say that plays the primary role. It's kind of the most overarching driving principle, but interactions with the stationary phase also have a place. Now, this particular slide shows that. So I always like talking about this particular figure. It's really, really cool. What this shows is two separations. Same sample, same exact sample components, just on two different columns. The first column is a PDMS column. That's that polydimethylsiloxane. That's where all the side groups were CH3. All of our R groups from that previous slide, just CH3 methyl groups, polydimethylsiloxane, right? This very nonpolar column, about as nonpolar as we can get. And the second section was on our PEG. This is our polyethylene glycol, or our carbowax column. This one's very, very polar. So we're running the same samples. Now, what we're going to do is we're going to consider this first chromatogram. Again, detector response versus time. No surprise, chromatogram, right? And what they've done, they injected the sample, multi-component mixture. This is the compounds which were present. And they've numbered the peaks. 1, 2, 3, just numbered them in order. 4, 5, 6, 7, 8, 9, 10. 10 compounds, right? So let's see what they saw. Well, what they found is that acetone was the first peak to elute, and pentane was second. Then propanol, methyl ethyl ketone, hexane, butanol, down the list, right? Heptane, pentanol, octane. So let's compare apples to apples. So what I would like to do is look for alkanes. Just alkanes in this list. Okay, here's one. Pentane, right? 5 carbon alkane. There's hexane, number 5. Okay, it's got 6 carbons, heptane, 7, octane, 8. So we have C5 through C8 compounds. What is their order of evolution? Pentane first, hexane, heptane, octane, obviously, right? Because we just numbered the peaks in order. Larger peak number, later eluting. What are their boiling points? Pentane's 36, hexane's 69, 98, 126. The boiling point is increasing as the later eluting peaks come off the column, or the boiling point increases as retention time also increases, right? So for these alkanes, we see this clear pattern. Higher boiling compounds elute later. And again, that's kind of our general overarching principle. Now, within this list, though, we see some compounds that are kind of out of order, like acetone, for instance. It's got a higher boiling point than pentane. That's a little confusing, right? Shouldn't acetone elute after pentane if there were no intermolecular forces at play? You might think that, right? But acetone has a C double bond O. A little bit more polar, so it's got a little bit higher boiling point, okay? But in pentane, our C5 hydrocarbon, that's completely nonpolar. That might have more affinity, perhaps, for the PDMS stationary phase, also nonpolar. Whereas acetone, really wouldn't have an affinity for that phase, would it? So we can start to see maybe how these intermolecular forces play a little bit of role, but with that said, that's kind of superimposed upon this general principle that high boiling point compounds elute last and low boiling point compounds elute first. That's our general guiding principle. And that makes sense because the higher the boiling point, that material is much more likely to spend more time in the condensed phase on the stationary phase and not vaporize. And if it's not vaporized, it's not moving in the mobile phase, it's not moving down the column, it's just standing still, right? All right, so interesting stuff already. But it turns out we're not done because the second separation over here on the right is on our polyethylene glycol. And this is a polar phase, our carbowax, right? They injected the same exact sample on this phase and got something completely different in terms of their separation and the order of elution. So let's dive into that. So first they saw peak number 2 eluted first, and then 5, 8, and 10. So 2, 5, 8, and 10. Whoa, 2, 5, 8, and 10. Where have we seen those before? Those are all of our N-alkanes, aren't they? They all eluted first now. Now, why was that? Well, our PEG column is highly polar, and these alkanes are completely nonpolar. They have no affinity for the stationary phase to deposit or absorb the stationary phase at all. The alkanes, they hit the stationary phase, say, hey, I'm not polar. I don't have any intermolecular forces with you. I'm just going to evaporate, go back into the gas phase, and percolate down through the column, be forced down through the column and elute. So while they still elute in the order of their boiling points, there's just no retention whatsoever to this PEG phase. They just move through the column quickly. Now, what do they see after that? Well, peak 1 is next. Peak 4, this is just the solvent, so we won't worry about that, okay? Peak 1 and 4, 7, 3, and 6. And 9, way out here, look, 18 minutes, there's a peak 9. So what do we notice about these really late eluting peaks? Let's highlight them in the list, okay? Pentanol is 9, 6 is butanol, 3 is propanol, okay? I keep seeing OL, don't I? What's that OL for in organic chemistry? That signifies what? An alcohol group, which is something that looks like this. Different structures for each one, but that's our alcohol group. And that is a highly polar group. And you've got hydrogen bonded directly to a highly electronegative element. That can undergo these hydrogen bonding type interactions, can't it? So these alcohols can strongly interact with our highly polar polyethylene glycol carboxylates and be retained. And that's what we see. Look, these alcohols are highly retained compared to everything else, aren't they? They're the latest eluting. And then here in the intermediate region, we have these other substances, 1, 4, and 7, which are acetone, ketone, and pentanone. Okay, so we have a bunch of ketones basically, which are also polar, so they're held back or retained a little bit by the stationary phase, but not as much as the alcohols. And this is all due to these intermolecular forces with the stationary phase. So I find this figure just really fascinating, okay? You can see that boiling point, kind of a key factor, particularly on the nonpolar column, higher boiling point, slower elution. And then on the other hand, over here, we can see how the intermolecular forces with the stationary phase are also important in retaining material. So depending on, if you choose a nonpolar column or a polar column, you can get different results. And of course, the way to figure out what a particular peak corresponds to would be running standards or pure compounds. You'll get the same retention time, or just about the same retention time. And that kind of gives you some confirmation that that particular peak is a particular substance, okay? But it's very, very interesting. There's another thing that's pretty interesting about GC as well. We can carry out what's called temperature programming. Now, I mentioned earlier that the temperature of our GC oven is absolutely crucial parameter. You need precise control over your oven temperature. If you can't achieve that, you are going to be in a world of hurt pretty quick in GC. Because if you change the temperature, you change the vapor pressure of your materials, and your elution behavior will be all over the place. Your retention times will change from run to run to run. It'll be a big mess, okay? But let's assume that your oven is of high quality and you can precisely control your oven temperature. What can you do with it? Well, one thing you can do is conduct what's called isothermal GC. In isothermal GC, the temperature is going to be the same throughout the run or the experiment, always the same temperature. Maybe you set it at 150 degrees and you leave it parked there the whole experiment, never changing it. But you can also run your experiment temperature programmed mode. This is where you're going to change the temperature during the run. Usually you increase it. You run a temperature ramp or gradient. So maybe you start off at 50 degrees at the beginning of your experiment, and you slowly increase the temperature at a fixed rate. Here it's 8 milliliters per minute, 8 degrees per minute, excuse me, up to 250 degrees centigrade. So you're increasing the temperature at a very specific rate. Now, you could choose to do a linear ramp at a constant 8 degrees per minute, 10 degrees per minute, 15 degrees per minute, whatever you choose, or you can increase it for a few minutes at a certain rate, park it for a while, increase it more at a different rate, park it, and then really ramp up. There's lots of different gradients that you can run. And it turns out that these ovens can be programmed, and the more complicated devices, the ovens can be programmed to achieve whatever temperature ramp that the user really wants to. So what's the big advantage of this temperature programming? It turns out there's actually a pretty big advantage. These figures over on the right show this. Now what we're actually looking at here is, again, running the same exact samples twice. One isothermal and one temperature programmed, okay? That's the big difference, the big comparison. But what exactly is this sample? Okay, well, the sample is a mixture of a bunch of different linear alkanes. What is that? Well, it's the carbon-hydrogen-based compounds, okay? This way, they contain various number of carbons. When the hydrogen, just make a long chain, okay? Increasing the number of carbons by one from one compound to the next. Okay, linear alkanes, we get that, right? So what we see here and all these labels are basically the number of carbons in that compound. So C8 is octane, for instance, okay? We have the C9, C10, C11, 12, and so on down the list, okay? Now notice that the later eluting compounds have higher number of carbon atoms, and that's to be expected, right? Because as we increase the number of carbons in our molecule, we're increasing the molecular weight, and as a result, that material becomes less and less and less volatile at its higher and higher boiling point. So these out here have high boiling points, and these over here have much lower boiling points. Okay, so not a surprise. We see smaller molecules eluting first. Now this is an isothermal run. And to accomplish this run, to even get the C15 peak out, we had to wait about an hour and a half. That's not so user-friendly, right? We kind of want to go to lunch at some point. Don't want to have to wait around lab and watch for this peak after an hour and a half. Can we do something about this? Well, we can. We can run isothermally, or sorry, temperature programming. Now in temperature programming mode, we're going to start off at a lower temperature, say 50. We're going to ramp it up to 250 at 8 degrees per minute. So we're slowly increasing the oven temperature. We inject our sample and we wait to see what we see. Now we get a peak at about 2 minutes. So that's the C6, the C7. There's our octane that we saw there, right? We C9, C10, C11, 12, 13, 14, 15, 16, 17, 18, 19, 20, even 21. And look, we're just a little over 30 minutes here, okay? So we had to wait an hour and a half to get the C15 peak here at isothermal. But gosh, a little over half an hour, I can get the C21 peak. I don't even see that here. Maybe I just gave up on the experiment, or maybe the peak just got too broad. It kind of blends in with the baseline. I couldn't detect it, but I can see a C21 peak here in just a little over 30 minutes. So, and the peaks themselves, gosh, they're tall and skinny. They look beautiful, don't they? These are beautiful chromatographic peaks. So why did this happen? Okay, well, I started off at a low temperature where I could sort of have some selectivity or differentiate between these low boiling point compounds. And by slowly ramping up my temperature, at a certain point, maybe say 20 minutes into the experiment, I could do the math, right? But at a certain point, the temperature of my oven started to be hotter than this 150 in the isothermal. It got up to 200 degrees, 220, 225, 250. At these higher temperatures, we are able to successfully volatilize these heavier compounds. And when they volatilize, they flow through the column out towards the detector, and we can make measurements of them, okay? So by increasing the temperature to higher temperatures, we were able to basically elute these quicker. We sped up the experiment and also produced these beautiful, beautiful chromatographic peaks, which are very, very easy to observe. We can get all the way to C21 in a third of the time. So temperature programming is a really, really good technique in GC. It's frequently used to obtain the highest performance. And don't be afraid to do this if you ever have to develop a method. There's only really one downside to it that I can think of, and that is at the end of your run, the conclusion of your run after you're done, you have got to cool down your oven and equilibrate your column back at the starting temperature before you can do a second run. Okay, and you have to do this every time. So that takes a few minutes at the end of the run. You got to wait for whatever time it takes to re-equilibrate at the new temperature. But that's really the only drawback. Okay, so I'm going to stop this video because we've been going about 50 minutes, and I like to try to keep them to a manageable length. And I'll come back with another one in a second.